Okay, we're recording. Hello, hope everyone's had a good week. There's been some exciting, I guess, or not exciting in the fun way, but exciting in the interesting way, news in the Ethereum world, which I'll talk a little bit about first. But firstly, thanks everyone for sending through your addresses. That's awesome, and hopefully we'll get a chance to use them today, and we can kind of all interact with the smart contract together, which will be really cool. But essentially what we want to do today is kind of really get into actually writing smart contracts. So we'll kind of go from scratch on a few smart contracts and write them together and kind of see how we go about designing programs that run on the blockchain and how we actually write them in the Solidity language. So again, if you've got any questions, put them in the chat or just interrupt me. That's all good. But otherwise, we will get started. So the news that I saw this week concerns a stablecoin called ION, or it might be IRON, I don't know what they call it, but we talked about stablecoins last week. So the idea is that they pick a real world currency like US dollar and they peg the cryptocurrency to that US dollar so that it will always stay at the same price. And we have the centralized stablecoins like USDC, which basically has US dollars in a bank account and it's linked to the cryptocurrency. So you've got that physical backing. Then you have decentralized stablecoins like MakerDAI, which uses smart contracts to kind of settle the price based on collateral. And so this ION stablecoin, which was at the time of this article worth 262 million US dollars, was one example of a decentralized stablecoin. And the idea was that you only needed like a small amount of kind of real world currency to back up this stablecoin and the smart contracts would work it out. But something really interesting happened last week where you can see the kind of total value of this stablecoin suddenly plummeted. And there's a lesson to learn from us when we start thinking about smart contracts in that it kind of shows how important it is to make sure that our smart contracts don't have any bugs in it. So the issue essentially revolved around this price here. The smart contracts that governed this ION stablecoin relied on something called an oracle, which is like a smart contract that's reading real world information. So it had an oracle that was reading the price of the backing currencies, the collateral. And that price, because people found some problems with this system, suddenly dropped towards zero. Right, so people thought that the price of the asset backing this stablecoin was worth $0. What that meant, or what that would normally mean, is that everyone would pull their money out of this, they would get their money back, and the stablecoin would just kind of cease to exist. But the problem was in their withdrawal function. So if I scroll down to here, just zoom in, you can see they had this line in their withdrawal function. So this is how you get your money out of the stablecoin. And here they've essentially said, we're requiring that our share price is greater than $0 or else it's an invalid share price, right? It's a little check they put in just to make sure that everything was working correctly. But what they either didn't anticipate or made a mistake when they were writing the smart contract is that the share price went so long that it actually went so low that it hit zero. So then anyone who tried to withdraw their money from this contract, suddenly this check was failing because the share price was zero, not greater than zero. So this should have been share price greater than or equal to zero. So because of that bug, 200 million US dollars was stuck in a contract, in a smart contract. So missing one character can have huge economic problems and can cost everyone a lot of money. So we saw earlier talking about Ethereum, like some huge hacks like the DAO hack, the DAO hack, and the parity hack, which lost, I think, 30 million USD. So it's really important when we start dealing with smart contracts and anything on the blockchain to double check for bugs. And we'll talk a little bit about how we can do that as well. But I just thought this was a good motivating example for us to be really careful when we work on smart contracts. So today, what we're going to be talking about mostly is a language called Solidity. So really kind of broadly, Solidity is the language that almost everyone uses to write Ethereum smart contracts. And because Ethereum is by far the most widely used blockchain for smart contracts, Solidity is then in turn the most popular smart contract language in the world. So the kind of, on the surface, it looks similar to C, JavaScript, Java, pretty standard imperative languages. And all, I wouldn't say even almost, I would say all Ethereum tools are based around using Solidity and writing a smart contracts in Solidity. So there are also a couple of other options if you're interested in kind of exploring different languages. So there is Viper, which is run by the Ethereum Foundation. So the kind of non-profit organization that looks after Ethereum has an alternative language called Viper. The main difference is that it's kind of based on Python. So it looks a lot different to Solidity. And it's got some kind of goals that are slightly different to Solidity. So it's not as widely used, but you can still write a proper smart contract in Viper if you're interested. Then there is also a language called Yule or Joule, depending on how you pronounce it. That's kind of a lower level, closer to assembly language that not a lot of people use unless you're doing really fancy stuff. But the kind of crux of the matter is we'll be dealing with Solidity for now.
Adel, I had a question.
Yeah, go for it.
Is there any language that is similar to Python by any chance?
Yeah, so Viper is based on Python. So if we look at Viper by example, you can see that it looks pretty similar. Like the functions are declared the same as Python, and a lot of the syntax is the same.
Right.
So if you're really familiar with Python, you can try Viper. And the Remix IDE that we were looking at last week also supports Viper as well.
Right, got it.
Yeah, and it's important to remember that Ethereum runs as a virtual machine. So no matter what language you write your smart contract in, it gets compiled down to the same bytecode or the same virtual machine instructions. So really you can write it in any language that compiles to EVM instructions will work. It's just that most people tend to use Solidity because it was kind of the first big language. So that's what everyone settled on.
Okay, got it.
If I do that, can you see the slides?
Yes, we can see the slides.
Okay. So what we'll start off by doing is I'll go through kind of the basic language features. And then I will talk a little bit about the kind of principles that we'll use to build smart contracts. And then we'll get into actually building some smart contracts live using that Remix IDE in a way that illustrates each of the principles that I'll talk about. But first, I think it's a good idea. We'll just do a little whirlwind tour of how to actually, or what features are available, and then we'll see how to use them a little bit more. So to put this in a bit of context, what we're going to be building, our first contract is kind of a smart contract that stores key value pairs. So you can say, have a key like name, and you can have a value like Cadle, and you can store these on the blockchain using our smart contract. So if we look at these three functions, this is kind of the interface for our smart contract. We think of a smart contract as like an object in an object-oriented programming language. We can also declare like an interface that describes how someone externally will start interacting with the contract. And the main operations that we're supporting are set value, so putting a new key value pair in, and get value, so reading the key. Right? It's pretty straightforward contract. There's one kind of wrinkle that I've put in just for illustration purposes. We'll have this list of reserved keys. And if anyone tries to set a key value pair using one of those reserved keys, it will fail. So it's not like a super useful scenario, but say you don't want someone using an L instead of an I to trick people. So you might block out that key that uses the L instead of the I, right? So looking first, let's kind of look at the interface here. We have a constructor. So this is a special function name. If you type constructor, this is the function that gets called when you create the smart contract. So here, when you deploy the smart contract, you have to pass in any arguments that are specified as part of the constructor. So here it's asking for a list of reserved keys or an array of reserved keys, and we'll talk about those data types in a second. Then the external interface from then on, once it's deployed, once the smart contract has been agreed to by everyone in the chain, We can set the value by passing in the key and the value, and that'll store it. And then we can read back the value by passing in the key. So that should be pretty straightforward. Now, I'll just jump to the end so you can see what the full contract looks like. So this is what we'll be kind of stepping through in these slides. So you can see it's super simple. It's like 20 lines of code at the most, but it will build out that smart contract that we can then deploy on chain. So starting right at the top, we have a single line here called the pragma. And using this line, we declare which version of Solidity we want to use. So this is pretty straightforward. I'm wanting any version of Solidity greater than 0.5. So right now we're up to 0.8 in Solidity. And people tend to specify the version explicitly because things change quite frequently. It's not yet at a 1.0 release. So every time this number increases, things break, and you have to kind of change your smart contracts. So it's a good idea to be explicit with the version you're using. Then what we want to declare is our contract. So the contract, as I said, is like a class or an object. You define your contract as a class of sorts. So we're saying our contract is called key value. And then when you deploy it to the Ethereum network, that's like creating an instance of your class, right? So you've created a new object on the Ethereum network called KV. And that object holds both state, so your data, and methods for interacting with that state. Generally, the way it's structured is we'll have our kind of contract definition. Then we'll list out all the different points of state in our contract, so the data it will store. Then we'll list the methods for interacting with that data. So here we go, starting off with the state for our contract. We're going to need two different variables. So this is the storage data that will go onto the blockchain because it's been declared in our contract. If we kind of look at this first definition here, you'll see that it follows a pretty standard variable declaration pattern. So anything that you define outside of a function goes into your kind of contract storage. And this is what gets stored persistently. So if I set a value and then I wait 3 weeks and read it, because it's in my contract storage rather than in my function, like intermediate storage, this will actually be saved on the blockchain. So all of these values will be added to the blockchain and kept there. We first declare the type of the variable. So if you've done Java, like this is easy for you, but if you've only ever used Python, you might not be used to declaring the type explicitly. You're just saying exactly what type of data can go into this reserved keys variable. So that's the name there. Then you have this visibility modifier in the center. So again, this is like Java. If it's a private variable, it can only be read by functions inside the contract. If it's a public variable, then you and I or anyone else with an Ethereum node can read it by interacting with the contract. So for the key value storage, we kind of have two state variables. Reserved keys, we want to hold all the keys that we're not allowing people to set. So maybe that's A, B, C. What we're declaring here is an array of something called a bytes 32. So bytes 32, as it's probably self-explanatory, is 32 bytes in a kind of chunk. So it might look something like this. Right, this here would be a bytes 32 value. It's 32 bytes expressed in hex notation. So each of these 2 characters forms 1 byte. And the reason why we have a special bytes 32 in Ethereum rather than just always using like a byte string of any length is because it's really commonly used for hashes. So we talked a lot about hashing in the first session. Oh, someone else has just joined us. So we use hashes to kind of connect our blocks together and so on. But we also use it a lot to store data in contracts and to interact with contracts. So Ethereum has given a special type, bytes 32, for storing hashes. Then we put this little this square brackets on it. So this is now an array of hashes. So we can have multiple in essentially a list. Then we have our second state variable is the values, and this is the actual storage of our contract. This is where we're storing the label into a value. And what we're declaring, or the type of this contract, sorry, the type of this variable values is a mapping. And a mapping is like a hash map or a dictionary in Python. It takes in a bytes 32, so a hash as its input, and it gives back a string. Right, so if I start storing values in this, I could say like A is mapped to Cadle, B is mapped to a leaf, and so on. And that's all stored in this mapping. And you can use mapping with pretty much any Ethereum type. So you could have, say, mapping a number to a number, or mapping a hash to an address, and so on. And for reasons that we'll get into, mappings are probably the most commonly used type for contract storage, because they tend to be really efficient, and they're a lot more efficient than arrays, which we'll talk about as well. So the kind of, I'll just briefly show the types before we go any further. Once you start writing your own smart contracts, this website will be essentially your Bible, docs.soliditylang.org, and search Solidity docs. And it's got a lot of information. So what I will do, just go to this type section. So these are kind of the basic types of data that we can interact with in smart contracts. So we've got Boolean, true and false. We've got a bunch of types for storing numbers. So you've got integers, which can be negative, and you've got uint, or unsigned integer, which can only be positive. So from 0 up. And the interesting thing about Solidity is you have to specify the length of your integer, or the maximum size. So if I wanted to say have an unsigned integer, so a number that can be 0, 1, 2 and up, I have to put a number after it that represents how many bits of length that integer will be. So a uint 8 can be up to 8 bits, which is then 2 to the power of 7 as the maximum. So basically you would use the smallest integer size that would fit the maximum number you're looking to store. So if I was only looking to store the numbers 1 to 10, I would use a uint 8. If I wanted to store 10 million or 10 trillion, I might use uint 256, which gives me 2 to the power of 256 as my top limit. And if you just write uint or int, it defaults to 256, right? That's the maximum. You've got as well addresses. So this holds an Ethereum account address. And if you want your contract to be able to send or receive money from this address, you have to make it an address payable. And we'll talk more about all of these, but just to give you a brief overview. We have arrays, which I'll talk about. We have strings, so you all know what a string is. We have enums, I'll talk about them too, but they're a set of values that we can use. You have functions. You have mappings. What else have we got? I'll just scroll through this really quick. And you have structs as well. So a struct is useful when you start to want to put a bunch of data into the same place, the object together. It's like it's like a dictionary in Python or a struct in C. So here we have our struct called struct type, and it has 2 variables inside it, which we can get to. We've got mappings. What else do we have? That's about it. So one of the things to note is that there's no way in Solidity to use floating point numbers. So that's any number that has a decimal point like 0.5. There's no native way to implement that in Solidity because it doesn't support floating points or decimal point numbers. The way around that is to use something called fixed point, which is what we were doing when we were talking about the ERC 20 standard. Essentially, we say we'll use a really big integer to represent this decimal number, and we'll just say that the first 18 numbers in the integer are the decimal places of our floating point. And you can modify the kind of maths as you would expect to make that work. Okay, so we've defined our variables. when we have our arrays, we can have them either be fixed size, so we can say we're going to have an array or a list of 5 reserved keys, and it's always 5 keys and it's fixed. Or it can be dynamic, so you can start adding more reserved keys and the length will increase. You start with a maximum of 1, you can go up to 1 billion theoretically if you wanted to. But there's different trade-offs when you do that. Most of the time, it's a good idea to make your arrays fixed when we're doing Solidity. And again, that's a summary of mappings. Okay, so let's look first at our constructor. Now remember, this is the first function in our interface. And the constructor is the function that you call to provide with data when you're deploying the contract for the first time. So when you're essentially instantiating your contract and deploying it to the Ethereum chain. Here, what we're saying is we're going to pass in an array of hashes of bytes 32, which is called underscore reserved keys. And then we're going to set our contract storage variable reserved keys to be this value that was passed in, right? That's really straightforward. Something that's interesting to note, and it's quite important when you start to optimize your smart contract costs, is that there's generally 2 ways to store data in a smart contract. There's 2 locations that it can be stored. And you can think of these as like the hard drive and RAM. So there's memory, which is your RAM. Anything that you write into memory and that you put into memory gets deleted at the end of the smart contract transaction, right? So you can use it for local state, for calculations and things like that, but it won't be left in the blockchain once that transaction finishes. Storage, on the other hand, is like your hard drive. So these are those variables that we declared in the top of the contract outside of the functions. And anything that's put into storage will stay on the blockchain until you delete it as part of another transaction. So here what we've said is that this array that we're taking in is going to be in memory. So it will be deleted at the end of the transaction. And that's why it's got this little underscore. So, it's kind of private, it's temporary. But what we're going to do is copy the memory array into this storage array so that it actually stays on the blockchain and we can use it later. So hopefully that makes sense. Now, public functions, can be called by any account, so the external user, whereas the private functions have to be called by another function in the same smart contract. Okay, so now let's unpack this second function. So this is set value. Here we take in 2 arguments. We have a hash, so the key, bytes 32, very easy. And then we also have the value, which will allow it to be any string. And again, this string starts off being in the memory. So it would be deleted at the end of the transaction if we don't do anything with it. But in this function, we're going to save our key. So when we set a value, there's really 2 things we want to do. The first thing that we want to do is make sure that it's not a reserved key, because remember we said that if we try to set a key that's reserved, we should reject that transaction, it should fail. That's one of the business rules of this smart contract that all the nodes in the network are working to enforce. So to do that, what we can do is use something called a require. And here you essentially use this require function. And then in here, you put anything that evaluates to a Boolean, so true or false. Here we're checking if the key that's coming in is reserved. And then we're negating that. So this will be, if it's reserved, it will be false. That would be true. And if it's not reserved, it will be false. And the idea is that when the require value, so when this is false, the whole transaction will be rejected. So if someone passes in a key that's reserved, so it matches something in that reserved key's storage value that we set in the constructor, it will be rejected by this line here. Then if not, we'll continue to run the transaction. So we just go to the next line. And here we're accessing that mapping that we declared at the top of our contract. And we are setting the mapping to be from the new key we're passing in to the value that we passed in. And then that gets put into the storage and that will stay there from then on. Okay, so then some more about requirements. So it's like an assert in C, or there's assert in Python as well. And then That's how the mappings work. That's fine. Okay, now let's look at get value. So this is the opposite of set value. We actually want to return some data from the blockchain. There's kind of two new things in the function declaration here. Firstly, we're saying that it is a view function. So we've added that on. It's still public, so anyone can call it. But we've added this additional modifier saying that it's a view. And you might remember from our token contracts last week, a view function is something that can't change the storage of a contract. So if you call a view function, you know that it's never actually going to modify anything about your contract. It only will return data. Then we use this kind of returns statement here to declare the type of data that's going to be coming back. So when we call get value, we pass in a key and it's going to return a string. Then, just like pretty much all languages, we just write return and then the value we want to return. So we're getting our values mapping, we're looking up by the key that's being passed in and we're returning that to the user. So that's all pretty straightforward. Okay, now let's look at this private function is reserved key. So it's starting to get a bit more complicated. We've used this is reserved key function when we're setting a value to make sure that we're not using a key that we can't do. So the idea of this function is we're going to pass in a key and we want it to return true if we've set it in our reserved keys array and false if it's not reserved at all, right? So just like all iterative languages or imperative languages, we have loops in Solidity. So we declare first our iterating variable I for as long as I is less than the length of the reserved keys array, we will increment I. It's very standard. Then if any value in the reserved keys array is equal to the key we've passed in, we'll return true. If this loop ends, we'll return false. So it's all quite straightforward. Because we've marked this as private, it means that it can only be called by other functions in this contract. You know, I couldn't call this is reserved key function as a user. So we've got for loops, they're the same as JavaScript. We've got if statements, they're also the same as JavaScript. So you can do if, else, so on. And so we end up with that final KV contract, a very whirlwind way. Are there any questions about that contract before we move on? And do it.
Oh, it's cleared. It's clear.
Cool. Awesome. If I'm over-explaining things too, let me know. I know you guys are all already developers. Okay. So in general, I think there are 4 principles that we want to use when we're developing smart contracts that makes them a little bit different from writing normal programs. The first kind of problem that we encounter when we're writing smart contracts is that the more computation we do and the more data we store, the more it actually costs to run our program. And that can be quite significant. So if you use, say, a big array and you have to loop over that array, it might cost you $10 to actually run that, as opposed to if you use the mapping, it might cost you 2 cents. So it becomes really important then to choose efficient data structures that allow you to do the computation and functions that you want your smart contract to encode in the most efficient way possible. Then the second kind of point that we'll also do as an example is that most smart contracts kind of operate like a state machine. And if you're not familiar with that, I'll explain what that means. But this is a really good way of modeling the smart contracts that you're designing. Then thirdly, what we want to do is amortize all work of the smart contract. And what amortize means is instead of trying to do all the work at once or all the computation at once, we want to split it up as much as possible. So instead of everybody, putting in data really cheaply and then one person at the end having to pay $30 to compute it all, it's much better if everyone has to pay 2 cents and then at the end the data is already in the format that you want it to be. So the idea is you're spreading the work and you're spreading the costs of your contract. And finally, we generally want to structure our interactions with contracts in this order. So conditions, what has to be true for us to do this thing. Say we want to write a token contract like we looked at last week. So the ERC20 token contract. We might start off with a condition that whoever's transferring $5 has to actually have $5 in their account. Then we do the effects. So this is the actual changes to our contract storage and changes to other contracts. Then finally, if there's any interactions with people, so sending Ethereum to someone or transferring them a token, we do that last. And that's for security reasons, and we'll talk about why as well. But what I wanted to do is kind of take each of these principles one at a time and kind of work on a contract that illustrates that principle really well. So what I'm going to do is firstly start off with this choose efficient data structures principle. And to do that, we're going to improve the KV or the key value contract that we've already got and kind of see what this means in practice. So to do that, I'm going to remix. And I know everyone sent their Ethereum keys, which is awesome. So hopefully you also had a chance to try out Remix. You'll have plenty of opportunity otherwise. But what I'm going to do is create a new contract to start. So just go file. I'm going to call this ukv.sol. So I will paste in that contract that we were looking at previously. Okay, so let me zoom in a bit. This is that contract that we're looking at before, just a bit trimmed. So it's got all that standard stuff. And you'll recall from last week that the general flow for testing our contract is to write it, fix any errors that this IDE gives us straight away. Then we'll go to the compile tab and we'll compile it into Ethereum bytecode. Then we'll deploy it onto our kind of test local network. And then we'll interact with it and make sure that things are working as we would expect. So I will compile it first, got no warnings, that all succeeded. Go to my deploy tab. I'm calling on the JavaScript VM. So this is the virtual Ethereum that's running in my browser. I'm not connected to a testnet or anything like that. And I'm going to deploy the contract. Now, because we have this constructor function defined that takes in data, in order to deploy this contract, I actually have to pass in some data this time. And it's asking me for a list of reserved keys. So maybe for the sake of illustration, I will have one reserved key. And let's say my reserved key is name. Right, so what I'm going to do is take the hash of that key, which is this. Now, the type of my reserved keys array is bytes 32. So I will put this in. What I've done here is I've just put a 0x in front of the bytes so that Ethereum knows to treat it as a bytes 32 as a hash. I'll do that deployment. Okay, so that deployment's worked, which we can see just like when we deploy the tokens. We can see that transaction has been successful down here. Look at the tick. And we can see the KV contract appear in our deployed contracts with two functions, set value and get value. That should all be pretty straightforward. One thing to note is that we're using hashes for the keys rather than the string. So we could technically have this type be a list of strings, and we could actually pass in name, location, right, rather than the hash, so like that. The issue is that if you use a string or a byte, so anything with a length that can be changed, you can't use it as the key in a mapping, which means that in practice, most people, if you're going to be using a mapping at all, you'll use a hash instead. That's just something to keep in mind. So we're using the hash. And because everyone agrees on the same hash function beforehand, everybody knows that this bytes 32 hash is equal to name on the chain. So you can hide that from the actual end user in your application user interface and so on. So it can all be kind of hidden, and you get that benefit of being able to use the mapping. So let's first try and set a value. So I'll put in this reserved key just so we can see what happens if I put in a key that's reserved. I'm going to try and set the name to be Cadle. So I'll send my transaction. We immediately get back this rejection. So we've got a red X. It says here, if you look in the small font here, you've got VM error, so virtual machine error, and it says revert. And revert is generally because you've hit one of these require statements and it's false. So if you're unclear why that's happened, you can also debug it and see, and we might use the debugger more later, but it's self-explanatory for now. What I will do is I will now set something that's not blocked, so location. And my location is Sydney. I'll send that, and that's immediately worked. So that data is now stored in the contract. And if we kind of think about the difference between memory and storage again, what's really happened there is that I called this set value function. It's passed in a key and a value in the memory. So the kind of RAM of the smart contract that's only there for as long as the transaction is running. But inside our contract, we've moved those values into the storage, which is declared up here and outside of the functions. So that even after that, this transaction is complete, it's ticked, it's been included in a block by a miner, it's been sent around the world, but that data is still there because it's in the storage section. And I can test that by using get value, putting in my key, clicking get value, and it returns Sydney. That's all working. Oh, let's set an image in the chat. So and I will send these contracts to everyone afterwards as well. They're pretty much adapted from the Solidity documentation. You can't put an address beside deploy. Oh, okay, cool. So if you look at the contract here, what I've done is I've chosen to be deploying the key value contract. So that's dropped down because I've compiled it. In the picture that you sent, you have deployed instead a contract called storage. And this is a default contract that's created a remix. So it's this one here, one_storage, right, which doesn't have that constructor function. So our KV contract, because we've compiled that, so we've clicked compile for kv.sol, it now appears in our contracts list to deploy. If I also compiled storage, so I've clicked onto storage, click the compile tab, compile storage, finally go back into my deploy section, and I'll see now that the storage contract is collected, I don't have that input, right? I can only deploy because there's no constructor. It just kind of remembers the last contract that you compiled and uses that, which is kind of annoying, but you have to, I guess, live with that if you want to use remix. So I'm switching back to KV, compile new KV, and now I can deploy it again. Hopefully that makes sense. Okay, cool. So what I want to do now is illustrate that first principle, which is about using the most efficient data structure for your application. And the kind of reason that we want to do this is mostly to save the execution cost. So remember that everything you do in Ethereum is paid in gas, which is then corresponding to an actual Ethereum price. And the more complex instructions you use and the more computation you do, the more gas that your contract uses in the transaction, and then the more you have to pay in the end. So what I really want to do is firstly kind of see how much gas this set value function costs currently, and then see what we can do to improve it. So if I run this again, I'm just going to set the same key location to be Sydney. And then I look down in my kind of transaction section, I can say the transaction worked. I'll just expand it out, and we can see that it costs 32,000 gas to run. Right, so we could calculate what that would be on mainnet. If I go to ETH gas station, my transaction calculator. I'm going to use this much gas. So with average price, then it's going to cost me that much, 0.002, right? So pretty cheap. If I wanted to be the fastest, then it would be double that. That's all. It's still pretty cheap in this example, but as you have more complicated transactions, it can get worse. But there are lots of ways that we can improve this value. And as a guiding principle, anytime we see a loop in Solidity, it's generally a bad idea. Because if we think about reserved keys, right, every time we want to set a value, we have to check that the key we're using isn't reserved. And to do that, we have to go through every reserved key that we've already got in the contract and make sure that it doesn't equal that, right? Which is what this loop is. We're looping over the array. If you think about one reserved key, that's pretty cheap. If we instead deployed a contract with 1,000 reserved keys and you had to loop over that every time, it would start to cost a fair bit of gas. So what I might do actually is, let's create a new instance. So I'll delete this already deployed contract. So we've got no more deployed contracts. And now I'm going to deploy KV again, but this time with a bunch of reserved keys. So I'll just copy the same one over and over, because that's easiest. So I'm just copying and pasting this bunch in the box. You can't see what's happening. I'll deploy that. Okay, so it took a lot longer that time, but we've got our key value storage there. Now we've forbidden location, we've reserved location this time. So I'm going to try and set a name. I'll set the name to be Cadle. 0x. Okay, so now we can see that it used a lot more gas. So this time, because it had to check all of those reserved keys, and there are a lot of them, this cost 351,000 gas while it keeps running this loop. And if we look at the gas station, that's now costing us about 10 times as much. So still not a huge amount, but a fair bit. But we've essentially built in a problem in the logic of our smart contract, in that the more someone wants to use this function, so the more reserved keys someone wants to add, the more it costs them, right? So it kind of disencourages people to use our smart contract. What we would like to do instead is find a more efficient data structure for storing these reserved keys. And you've probably guessed by now, we'll use a mapping for it. If you think about kind of algorithms, I'm not sure if you guys have heard of Big N or Big O notation. So the idea is that you can quantify how computationally expensive something is in a way that can be generalized across situations. So if we think about an array and we want to find a value in it, like we've got an array that looks like this. If we're looking for, say, 1, and we start looping through our array and checking all the values, we find it straight away. But the worst case scenario, so the worst case scenario here is we're trying to find 11 and it's not in there at all. But to know that 11 is not in this array, we have to check all of the items, right? So we have to check 10 items. If we know that there's n items in this array, so n here equals 10, but this could be 1,000 in the case of our reserved keys. What we're saying is, in the worst case, we're going to have to do n computations, and we call that
time complexity would be big O of n.
Exactly. Yeah. Yeah. So think about time complexity. Searching an array is O(n).
Right.
Cool. So you guys are familiar with that. Great. In a mapping, to look up something and see if it's in the mapping, it's O(1). Right. What that means is no matter how big the mapping is, it takes exactly the same amount of time. It's really efficient. So for this is reserved key check, what we want to do is convert our reserved keys array into a mapping so that we can make this a lot more computationally efficient. So to do that, I'm going to change the the value of my storage variable, reserved keys. I'm going to change the type of it, sorry. I'm going to change it from a bytes array to be a mapping from bytes 32. So that's what we put in. And then we're going to map it to a Boolean. And the Boolean is true or false. So what we'll say is any key, if it's reserved, it will map to true. If it's not reserved, it will map to false. And in Solidity, mappings have kind of a default value that depends on the type you put in. So if you have a mapping that goes to Boolean and you look up something that's not in that mapping, it's always going to return false. So by default, no keys are reserved, which is what we want. Now, what we're going to do is we have to kind of front load some of the work of creating this mapping. Because a user can't pass in a mapping type because of language restrictions, they can pass in an array, but they can't pass in a mapping. You can only use that inside the contract. So we won't change how the constructor kind of functions from a user perspective. They'll still pass in the array, but we will change how it populates this mapping. So what I'll do is I'm going to use a loop in the constructor. I'll loop through all of these reserved keys and I'll fill in the mapping in the constructor. So for loop, I'm going to use the biggest integer I can get, which is an unsigned 256-bit integer. Set to 0. It's the same as the loop down the bottom. So we're going to loop through all of our reserved keys that are coming in. I'm going to get the length of it with dot length. We go ++. So all the operators are the same as most languages, right? ++ is just increment by 1. You can get the length of an array with dot length. Then I will, for each of these values, I'm going to store it into this reserved keys without the underscore. So the reserved keys in storage. I'm going to put in the brackets the key. So this is of types bytes 32, which is equal to underscore reserved keys I, right? So the I, we're looping through the underscore reserved keys array. We're putting into the reserved key mapping. And that's going to be equal to true because it is reserved. We can delete that. Right, so we're filling in that mapping in the constructor. Then we can make this is reserved key function a lot more efficient. All we have to do is return reserved keys and look up the key, right? This is going to be true if it's reserved, false otherwise, and we can delete this whole loop. What we've essentially done is made this whole is reserved key function O1, and if we deploy it again, we'll see how much more efficient that is. So I will save this, it'll compile the new version automatically. Now again, I will create a new contract that this time has the same amount of reserved keys, and then we can compare the gas cost. Just do a bunch again. Again, I'm copying heaps in. Let's deploy this. It's a bit slow with that much data. Let's see how it goes. Cool, so that's deployed there. We can see we've got our old version here and we've got our new version here. So this time I'm going to use set value on the new version. And last time it cost 351,000 gas. This time, oops, I'm going to do the exact same call. There we go, and we see it, and it costs this time 48,000 gas. So we've pretty much divided it by 6. And that's already a good cost saving for the person who's using it. But even if I put in 1 million reserved keys, that cost will stay exactly the same. So it's now constant rather than dependent on the length of reserved keys. And so when we're talking about using the most efficient data structures, this is the main reason why. Otherwise, things can get really expensive. The other kind of interesting limitation of smart contracts is that it has a gas limit. So your contract can only use up to a certain amount of computation and then it's killed. And the reason for that is because otherwise someone could kind of lock up the whole Ethereum network. This language is Turing complete, which means it can simulate any program that would run on a Turing machine. What that really means in practice is that I, as a smart contract developer, could theoretically write a smart contract with a loop that goes forever. So it'll be like for uint 256 I equals 0. I just go true here, right? So it's going to run forever. I plus plus. And then deploy this to the Ethereum blockchain and then call a set value transaction. Remember, the way that Ethereum works is that if I call set value on a contract, that function gets run by every node in the network, right? So everybody's running this set value function to validate it. If there was an infinite loop that was allowed to run forever, it would just clog up the whole network forever. Everyone would be stuck on running set value for 10 years, right? It would defeat the whole network. So the way around that is that the Ethereum developers set a gas limit. I'm not sure the exact value. I think it's something like 6 million. We can look that up. Ethereum transaction gas limit. It's up to 15 million. There you go. But you can imagine that after 15 million, it will just cut this transaction off and revert it. So even if you're not a malicious developer, even if you're not trying to attack the Ethereum network, you could get into a situation where you accidentally make a contract that can't be used. So if we still had our isReserved key function looping through that array to check the values, and we added in, or we had a function that would let us keep adding in more reserved keys, we might accidentally add in too many reserved keys and then make it so nobody could ever call set value without hitting that gas limit because we have to go through all the keys. However, if we transfer it to this kind of mapping function, because this is O1, so it won't grow in complexity the more data is in the mapping, we kind of avoid that problem of ever hitting the gas limit. So you have to be really careful with the data structures you use. And in fact, it's usually a good idea when you are developing a smart contract to start with kind of thinking about the data you're using rather than the functions that interact with that data, putting the data into the most efficient format, and then tailoring how you access and how you modify that data based on how to do it efficiently. You know, when we're doing traditional development, like an app, we might start with the function that we want. So we'll start with, you can create a new trip in Uber, and then we think about the data later. But you kind of have to turn that on the head when we have this gas limit and the gas costs, because otherwise it can get really inefficient. Okay. Now, one other limitation with this contract here is that it's currently kind of public for everyone. So because I put public on all of these functions, that's not just me, you know, as the creator of the contract, I can access this and I can set a value and I can get a value, but so can literally anyone else with an address on the Ethereum network. So public means, you know, it's fully available to everyone. What I might do is I might instead have a requirement where I can set a value and nobody else can set a value, but anyone can get a value. So I want to start adding some access control to this contract. And in practice, you know, the vast majority of contracts are access controlled because it doesn't make sense for anyone to be able to call the admin functions, for example. So what the Ethereum developers have done is they've added in a kind of special type of function called a modifier. And a modifier lets you kind of transform an existing function to add more data to it or to add more functionality to it. And that is a bit confusing, but let's say we have a requirement now that set value can only be called by the admin, right? So the kind of first step of that requirement is, let's think about the data required for this feature. If we want to require that set value can only be called by the admin, we'll need some way for the contract to know who the admin is. Right, so what I can do is I can say, put in a new storage variable, and I'm going to say it's an address. I'll make it private, and it's called the admin. Right, so this is now a type address, which is any Ethereum address. So the actual user account will be stored in this. Then what I want you to do in my constructor is actually fill in this admin. Right, so in here, I could put any address. So I could put my address like that if I wanted to. But to make this contract more general, the most common thing to do is to set it to whoever actually deployed the contract. So whoever created the contract should be the admin. And Solidity provides us access to a lot of special variables that refer to blockchain information. In this case, what we want to use is something called message.sender. And it's highlighted differently because it's a special variable. This is the account of whoever sent the current transaction. So because when I'm calling the constructor, I'm deploying it, whoever is deploying this contract is going to be set as the admin, which is really helpful. And if you look in the Solidity documentations, in the sidebar, there is a section called units and globally available variables. And if you click on that, you'll get a huge list of all of these special variables. So message.sender, and you've got maybe the current gas price, right? So how much your gas is going to cost. You can actually, inside your contract, see what the current gas limit is. So you'll know when it's going to terminate. And you can see the block that it's been included in and so on, right? So all of these are quite useful, and we'll use some more of them later. But for now, we'll just use message.sender. Right, so now we have our admin stored. Next, what we want to do is implement the kind of restriction on set value to require it to be an admin. So you could do it just like this is reserved key function, right? Remember, we want to structure our functions as kind of conditions, effects, then interactions. So if we decorated it, it would look like conditions here, then our effects. We don't have any interactions yet. So we could just do this. We could go, I'm going to require the message.sender. So whoever's sending this transaction is equal to the admin of the contract, right? And this would work. This would block anyone who's done admin from calling. You can also, if you're using require, make it a bit more user-friendly by adding a string that describes the problem. So you write, user is not an admin. Now, if someone who wasn't the admin were to try and set a value, they would get this back as the error message rather than just saying revert. So that's quite helpful. And we might add that for reserved key actually too. Our key is reserved. Okay, so we could do that. Then we might say, and that works fine for this use case, but maybe we add a function that is to add a new reserved key. So we'll call this function add reserved key. It'll take in a key, which is the hash, and it will be public, so people can call it. It's not just inside the contract. And what we're going to do is go reserved keys underscore key equals true, right? So we're adding a new reserved key. And that's super simple as well. Obviously, we want the admin to be the only person who can add more reserved keys. So we could copy and paste this require statement. Right? And in a simple contract, that's an easy way to do this, these conditions, right, which are pretty common to all smart contracts. But the issue is maybe you have 20 functions that all require this check, or you have a bug in one of the checks, and then you fix it in one check but forget to change in all the others, right? So it's quite error prone. What we want to do is find a way to take this condition and make it generalizable and then use it for the functions or attach it to the functions that we're interested in. And to do that, we'll use the modifier. So a modifier is just like a function, but we declare it with modifier instead of function. So I'm going to call my modifier only admin, like this. And in the modifier, I can put those conditions that I'm interested in. So I'll move in this requirement to be here, right? And I'll delete it from add reserved key as well. Then what I'm going to do is add only admin, add this modifier to all my functions. And to do that, I can just add it like this, right? I can add it as a keyword after the function. So set value can only be used by an admin. add reserved key can only be used by an admin, and get value can be used by anyone. I want anyone to be able to read it. So that's cool. There's only one more step, and that is to tell only admin how to interact with the rest of the function. All right, so what we want to do is we want to check that the person sending the transaction is an admin, and then run the rest of the code of the function. And that will be different depending on what function it is. In a modifier, all we have to do is add an underscore like that. And now what Solidity will do is for anything that has the only admin modifier, it will add this line, and then where the underscore is, it will replace it with all the code of the function. So this is kind of taken that require out of all of the functions, put it in one place, and now we can really easily add that admin control to it. And what I'll do now is I will deploy the new value one more time, deploy the new contract one more time, and we'll see how that looks. So I'm going to clear all the other contracts. I'm going to say there's no reserved keys to start with. I'm going to deploy this. And now I'm going to start off by adding a reserved key as the admin. So I'll go to my cache. So I'm going to use this new add reserved key function. It just takes in the key that should be reserved. I called it and I didn't put the 0x at the start again. If you ever see something that says like error encoding arguments, just check the actual type of the argument that you passed in. If it's bytes, it always has to have a 0x so that Ethereum knows that it's a hex value. So I'll run that now. Okay, that was successful. Now, if I try and do the same thing, but I'll switch accounts. So I'll go from my admin to someone who's not the admin at all. I call add reserved key, and I can see that it's failed. And now I have this kind of helpful error message, user is not an admin. Right, so we can add kind of additional conditions using modifiers that can like kind of lock down our contract and make it more robust. Okay, and that kind of concludes our first contract that we're going to look at today and in this course. So are there any questions on this contract before we start moving on? Okay. So that was our first contract, and that illustrated the principle of choose efficient data structures.
Hello all, welcome to Let's Hear. If you haven't subscribed to our channel,
I'm sorry, what was the question? I heard if you haven't subscribed to a channel, not much more than that. Might have been a mistake. Okay, I'll continue that. So that illustrates choose efficient data structures. What I will talk about next is the amortized work principle. So probably in the wrong order. But remember, we're talking about amortizing work as spreading the load out. So spreading the computation out so that everybody is kind of contributing a little bit of the cost rather than one person taking on all of the cost. And to illustrate this principle, we'll start over with a brand new contract that kind of does something a little bit more interesting. So what I'm going to do is again create a new contract, and this one I'm going to call simple auction. And what we'll build now is a smart contract that kind of lets us run an auction on chain, right? So think about a house auction. Everybody who wants to buy the house all keeps putting in their bids, and then whoever puts in the highest bids, the highest price they'll pay for that house, actually, wins the auction, bids the money. Nobody else has to pay, right? So what we want to do is take that concept and move it into the smart contract world. So what I'll do is first I'll just copy in something. Let's start off by looking at an interface. So I talked before about contracts. What you can do in Solidity is you can also declare an interface. And in the interface, we give the description of the functions and events in that smart contract, but we don't implement them, right? So then an ERC20 token, right, implements the ERC20 interface, and our auction contract will implement this simple auction interface, and it has to fulfill all of these functions and events. Right, so let's kind of look at the three functions we're going to be using in our auction. Each person on the, or each user who wants to bid on the auction can call this bid function. We've added this additional modifier here called payable. And what that means is that when someone sends a transaction that calls bid, they also send any amount of Ethereum, so the Ether currency, and that is paid into the contract. So if I want to bid $5, I actually have to pay $5 into the contract when I call bid. Then if someone else, so a Leaf, wants to pay $100, he wants to beat my bid, he's going to pay the contract $100. Then at the end of the auction, anyone who has lost, who doesn't have the highest bid, can call this withdrawal function and get back their money. All right, so hopefully that's pretty straightforward. The only extra thing, we'll have this auction end function, and anyone can call this when the time period of the auction has elapsed, and that will kind of close out the auction. It will transfer ownership of the house or whatever it is to the winner, and it will let everyone else withdraw their bids. Okay, so what we'll do first is we'll just kind of build this contract in the simplest way possible, and then we'll talk about how we can improve it by spreading out the work. So I'll start off like all contracts by just giving it a name like this. So I'm declaring a new smart contract. Now, because I want to say that it implements this simple auction interface, I can write is simple auction like this, and it will kind of tell the compiler to check for all of these functions in my auction contract. And if I had multiple interfaces that I wanted to inherit or for it to implement, I can just add them with a comma. So I could have two interfaces here. I could say have a simple auction interface, and I could have a simple auction events interface like this. And I could inherit both of these, right, if you wanted to start splitting things up. So you might have a contract that is an ERC20 token and is also an auction, right? And you can start to add more interfaces like that. Okay, so the first thing I'm going to do is I'm going to declare my data. So when we're thinking about an auction, one of the most important things is who gets paid at the end, like who's actually selling their information, or who's selling their product, the house in this case. We call that the beneficiary, so the person who's receiving the money at the end. This will be an address, it'll be public, and it will be called beneficiary. That's straightforward. There's one little complication. Because we want to pay them Ether, like we want to pay them actually Ethereum currency at the end, we'll just make this an address payable instead of an address to make sure our contract can actually send them the money. Then in auctions, we usually have a kind of time period the auction runs for, like on eBay, it might be 2 weeks. So what we'll do is we'll have a timestamp or a time when the auction ends. And then whoever sets up the contract can kind of say, I'm starting the auction now, it ends in 2 weeks or whatever, and we'll store that end time in storage as well. To store time on Ethereum, what we usually use is something called Unix Epoch time. And that looks like this. So I'm going to go Unix Epoch time. It's essential. This is the current Unix Epoch time. You can see that. And it's the seconds since some day in 1970. January 1st, 1970. The current time is how many seconds have passed since that date. Right? So it's a not very human-friendly way of specifying time. But what it means is you can put it into an integer like this, and it works for computers everywhere. You know, you can change it to your local time zone. You can display it however you want, but there's no confusion about it. So we use Unix Epoch times for time in all smart contracts. And To do that, we'll just store it as a uint, unsigned integer, called public, and we'll go auction end time. Right, and this will be the time when the auction ends. We also want to know when the auction has ended so that people can start to withdraw their failed bids. So what I'll do is I'll have a Boolean and I'll call that ended so people can check if the auction has ended or not. Okay. Now what I might want to do is I want to store all of the bids that we've got. So I will have a list of people who bidded, or an array of people who have bidded on the auction. So that's an address array, public bidders. And I'm going to then have a mapping from the bid and the bidder address to the amount they've bid. Like that. All right, so with a list of people who bid and then how much they've bid. And that's all we really need to store that. You can, if you get tired of typing out public, if you're dealing with state variables that go into the storage, public is default, so you can actually leave that off. But I find that in smart contract development, anything that you can specify, you should, because otherwise it's easy to make mistakes. We'll do public bids. And then what we're going to do as well is, actually, I'll add that later, but that's all we need for now. So what we want to do is start to implement this simple auction interface. But one thing you'll notice is that we don't have a constructor specified in the interface. So we don't have a way to deploy this contract. That's because it's impossible to specify that in a Solidity interface. You kind of just have to implement it in your contract. So what I'm going to do is create a new constructor. Like this. So I've just declared that definition. And there are kind of two things that we want to store in the constructor, so that we want to provide when we create the contract. The first is how long the auction should go for. And we'll pass this in as a number of seconds, and we'll call it bidding time. Then we will pass it in the person who should receive the funds, so the beneficiary. And that will be address payable beneficiary. Now, the reason I keep putting underscores in front of these is not for any technical reason. I like to do it for my function variables because I know that they will be destroyed at the end of the transaction, right? So I know that if it's got an underscore in front of it, I have to store it somewhere or it will be lost. It's just a convention that I and a lot of other Solidity developers use to make sure you don't get confused between, say, the underscore beneficiary that's in the memory and the non-underscored beneficiary, which is in the storage of the contract. So it can be handy. Beneficiary is really easy. We'll just move it into storage like that. For the auction end time, we can calculate that. So what we want to do is kind of fill in the current time and then add on the bidding time. So it'll be something plus bidding time in number of seconds. To get the current time, we can kind of refer to our units and globally available variables in Solidity. And we will see that we've got this block.timestamp variable available. And this will give us the current time in the block that the transaction is included in. So I can use that. I'll go block.timestamp. So I've just saved this and the compiler's flagged some errors here because it should look like this. I must not have run this contract here. So I'll talk about why this is happening. Okay. So we've compiled this. We've got this little red warning. And what it's saying is that we are missing the implementation of these functions from the interface. So we still have to implement bid, withdraw, and auction end. Right, so one of the benefits of using interfaces is you'll be warned if you haven't fulfilled that. So let's move on to bid then. This is really easy. What we can do is start off by just copying in the function from the interface. and then we'll add our actual definition like this. If I save this, I'll see a warning pop up. And if we look at this, we can see the type error is here. Our overriding function is missing override. And because we are creating a new function called bid, which is implementing this one in the simple option interface, we have to write override like that to tell the contract to override the interface's default function. Now, the reason we're using external here instead of public is because external is slightly more strict. What public means is the function can be called by any user, so any external account, but it can also be called by any contract. Right? So a contract already on the chain can call a public function. External means that it has to come from a user-facing account. So my account, your account, any node's account, but it can't come from another contract. So it's a bit more strict. Okay, so to implement bidding, what do we have to do? We have to check that we can still bid. We're still allowed to bid. So the auction hasn't ended. And I'll just put in these requirements as comments for now. So I can do a comment with 2 slashes. I'll go as auction ended, right? That's our first condition. And let's mark these as conditions. Has the auction ended? Is there already a higher bidder? If there's already a higher bidder, right, I shouldn't be allowed to bid less than that because there's no point. So we'll check that as well. Then if those conditions are successful, so if I'm allowed to bid, it's a valid bid, it's the highest so far, I will actually do my effects and I will store it. So what I'm going to do here is I will store my bid. And then interactions, we're going to have our first interaction here. And then what we're going to do is we're going to create an event describing the bid. And I'll show you how to do that in a second. So hopefully that makes sense. Let's implement each of these requirements in order. Again, this will be quite a simple contract. So has the auction ended? This is quite easy. We're going to do a require here. And what we're going to check is the current time is less than or equal to the end time of the auction, which we already have stored. So we go block.timestamp, which is the current time, is less than or equal to auction end time. If this fails, we'll give a helpful error message. We'll say auction has ended. Okay. Now, is there a higher bidder is a little bit trickier because we need a way to know who the highest bidder is currently. What I'll do for now is I'll just create a function called getHighestBidder. So we'll implement that function in a second, but essentially it's going to return the address of the highest bidder. And then I will find the highest bid by looking up in our bids mapping, the address of the highest bidder. And that will be the highest bid then by definition. Then I can finally add in that require that our bid, so the amount that we're sending, is greater than the highest bid. So we want something greater than the highest bid, or else we'll reject it. Our bid is too low. Okay. So how are we actually going to be passing in money or ether to our contract? Because this is a payable, you can actually send ether along with your transaction. And to get the amount that you've sent, we can use another special variable, this time message. So still like message.sender, we're using message, MSG. We're going to use message.value. And this will be the amount of ether that we've sent along. So we're going to require that we have sent more ether than the current highest bid. Okay, easy. That's our conditions done. Now, once this is all passed, we know that we're good to go. All we want to do is we want to store our bid. So we're storing our bid in these two variables. We've got our list of bidders and we've got a mapping of their address to their current bid. So the first thing we'll do is we'll add whoever this is to the bidder array. Now, remember we talked before about how there are kind of static arrays that may say have only 5 values and that's it. There are also dynamic arrays which can change size. And by default, because I haven't given this one an actual size, this bidders array can constantly grow as much as we want. To add a new value onto the end of the bidders array, I'll just go .push. And this is the same as JavaScript. In Python, it's .append. And in Java lists, I think you can do .push as well. I'm not sure. But we will add message.sender. So message.sender is whoever's sending this transaction, the bidder, to the bidders array. Then we will also add the bid amount, so the message.value, which is how much Ethereum they've sent, to this bids mapping. So the bids, I'm going to map their address, message.sender, to the value they've sent. All right, that's all we need to do to store that bid. Now, what we want to do is we might have, so I've got an issue here. We're expecting a semicolon. I've missed a semicolon on this line. So we need to end all our lines with a semicolon. And I've probably done it somewhere else. We haven't implemented get highest bidder yet, that's why. That's all good. Now, in the world of smart contracts, a lot of the time, people are interested in what's going on in the contract. So when we're looking at the tokens last week, we're interested in who was transferring to who was approving who, and so on. A way to notify people when things have happened rather than them constantly having to go to the contract and check is to use events. So we saw in the token there was a transfer event. In our auction contract, we have two events that we're creating ourselves. One is called highest bid increased. And what we'll do is we'll use this to notify anyone who's interested in the auction and let them know that there's a new highest bid. And if they still want to win the auction, they're going to have to bid more. Right? So in this interaction section, here's where we do things that kind of interface with the real world. And creating an event is one of those. So to create an event, I have to use a special keyword called emit. And emit is just like send out the event. I give the name of the event that I want to use, highest bid increased. And then the event takes in parameters just like a function. Right, so highest bid increased takes in the address of the new highest bidder and the amount they bid. So in our case, that is message.sender is the new highest bidder and message.value is the amount they sent. Right, so just like that. And with that, we have implemented our bid function. Now, are there any questions on that so far? Before I continue? Okay, let's keep building this. What I will do is I'm going to fix this error here, right? I haven't implemented get highest bidder. I'll do that now. So get highest bidder is a function called get highest bidder. I'm going to make it private. It's only available to use from within this contract. It doesn't change any state, right? I'm just reading things. So it's a view. And it's going to return the address of the highest bidder, like this. So to implement this, what I need to do is look through all my bidders and find the current highest bidder, right? So this is a really simple loop. And you might also already see where we're going with this example when we talked about replacing loops with mappings, but we'll see how that works. So UN256 bid. And then what we're going to do is loop through all of our bidders. So we'll go, well, I is less than bidders.length, I plus plus. Go, scroll up. If the bid of the bidder we're looking at is greater than the current highest bid, then we'll change the current highest bid to be that new one. So this is really simple. Highest bidder is that bidder. Okay. And finally, we'll return whoever we ended up identifying as the highest bidder. Okay, so that's implemented that get highest bidder function. Something to note is, again, we didn't give initial values to these two variables. So we've just declared the type and the variable. So these get filled in with the default value for that type. Highest bid, because it's a number, its default value is 0. So if we find any bid greater than 0, it will start to be increased. So this should only increase. And then we return that highest bidder. So we now have 2 more functions to go. We need to implement still withdraw, and we need to implement auction end. I might do auction end first because that's probably the next logical step. So we'll go up to our interface. We can see that auction end is just here, and we'll copy that down the bottom. I'm going to start implementing it. So in auction end, again, we're going to follow that same pattern. Conditions, effects, interactions. Conditions are, when can we call this auction end function? So we want anyone to be able to end the auction once the bidding period is up. So I'm going to say, have we reached the end of the bidding period? That's a condition. We also want to require that the auction hasn't already been ended, right? Because we don't want someone to keep calling auction end and keep transferring money to the beneficiary. So we'll go, has the auction already ended? Okay, that's our our conditions. Then in the effects, what we're going to do is we might want to, what are we going to do? We will find the highest bidder, as in the winner of the auction. We're going to allow everyone else to withdraw the money they've spent, so they can actually get their ether back. They didn't win the auction, so they're going to withdraw it. Then what we'll do is move on to our interactions section. So this is interactions with the outside world. Here we are going to transfer the winning bid to the beneficiary, right? The auction has been done. So because we're transferring to an account, that goes into our interactions section, right? We're interacting with something external to this contract. And what we also want to do is emit an event telling people that the auction has ended. Okay, so these are our conditions. And then again, we'll follow the pattern. We'll start implementing them from the top. So have we reached the end of the bidding period? We're going to require that the current timestamp is greater than the auction end time. Oh, that's easy. I'll go auction has not yet ended. Otherwise. Okay. We're going to make sure the auction hasn't already been ended. So we did have this ended value here, which will be default false. So we can check require not ended. I'll just give the user a note, auction end has already been called. That. Okay. To find the highest bidder, we will just use the exact same lookup we had here. So we'll copy this in. So we've now got the highest bidder and the highest bid. For everybody else, we want to allow them to come in and withdraw their bids. And this is a really common pattern in smart contracts. We could theoretically make the smart contract transfer the money directly to everybody who hasn't won. So we could loop through all the people who haven't won and send that Ethereum to them. But the issue there is that if there's a lot of people who haven't won, then this function, this auction end function, is going to do a lot of work. And that means that whoever calls the auction end function to finish the auction has to pay for the gas to do all that work. And remember, we talked about the third principle being we want to spread that work out as much as possible. A simpler way to do this is to kind of allow whoever sent their bid to pay the gas fee to withdraw only their bid, right? So we're spreading the work amongst all the people. So what we're going to do is use something called the withdrawal pattern. Right? This is just like a standard in building smart contracts. And we've already created this. Oh, we actually haven't created that. Cool. So what I'll do, in order to do the withdrawal pattern, we need to keep track of how much money is available to withdraw and who's already withdrawn their money. Withdraw their money. So we're going to add a little bit more data to our smart contract as well. What I'm going to do is I'm just going to add another mapping here. that goes from an address to a amount to return. So I'll call this pending returns. Right, that's all we need. When the auction ends, we want to fill up this mapping with all the money that is available to be withdrawn. When someone actually withdraws their money, we want to update it to be 0. Right, hopefully that makes sense. So go back down to here. We're going to fill up that withdrawal array now. So what I'll do is I'll really simply loop through the bidders and fill in that mapping with anyone who hasn't won. 4, 2, 5, 6, 0. I is less than bidders of length plus. I'm going to check if the bidder isn't the winner, right? So all non-winners, we're going to allow them to withdraw their money. So we'll set the pending returns value to be, or to add on their current bid, like so. Okay, so that's the effects section done. We've gotten the highest bidder and we've allowed everyone else to withdraw their bids. Then we're going to move on to our interactions. So here, firstly, we want to transfer the winning bid to the beneficiary. To do this, we're going to send the money in the contract from the winning bid to the external address that is receiving the money, the beneficiary. To do that, we can use a function that's available on all addresses. So remember, we've declared beneficiary as an address payable type, which means that we can send ether to it. So we'll go beneficiary.transfer, and then we pass in the amount of ether that we want to move from the contract to that account. And that will be the value of highest bid. And that'll transfer that winning amount to them. Then they could, give whoever won the keys to the house that we're auctioning off. And then finally, we'll emit this auction ended event, which takes in the address of the winner and the amount that they won with, the winning bid. So here we'll go highest bidder, highest bidder. And again, we're missing that right here. So go through the right like that. Okay, so now that is our auction end function, which is not too complicated yet, which is good. So we have one final function to implement. And if we hover over this, we'll see we are missing withdrawal. I'll grab this. And I'll go through this one quite quickly. We should all have the hang of it by now. What we want to do when we withdraw is we are going to check if there is money to withdraw. Or to be more precise, is there ETH to withdraw? If so, we're going to do an interaction and we're going to send and then we will mark the withdrawal as complete, so they can't keep withdrawing more money from it. And there is already a problem in our requirements here, which I'll talk about as well. So conditions, is there ETH to withdraw? Easy, we'll get the amount that the sender, so the person calling this, has available in their pending returns. So their amount is pending returns, message.sender. Cool. Then we'll actually send it. So we'll go, require amount is greater than 0. All right, so if the condition's done. Now what we want to do is we're going to go message.sender.send, and here we're going to send them the amount of ether that they have available to return. and we'll immediately see this kind of error. If you look at the type, you can see that message.sender by default is an address. In order to actually transfer any money or ether to them, we have to convert it into an address payable. So you can really easily just do this. Cool. Now, what we've got is another warning. And this is saying that when we use send, it works pretty much exactly the same as transfer, except that it might fail. So in transfer, we're saying that if beneficiary doesn't exist, or if they, for some reason, can't receive your money, we're going to fail the whole transaction. In this case, we're using send, which if it fails, if it can't send the money, it's just going to return false rather than reverting the whole transaction. So we might wrap this up in an if statement like this. So if the send doesn't work, then we will refill the pending returns like this. So we say, okay, that failed, give up, we'll try, they can try again later. I like that. Okay. And then we will return, otherwise we will say that pending returns for the message.sender is now 0, like they've completed the return and it was successful. Cool, so that is our withdraw function. Now there is one issue with this. If anyone can spot the ordering issue and put it in the chat in the next 15 seconds, I'll be impressed. Otherwise, we'll go through it. Okay, so the issue with this function is we have violated the most important rule when we're making these functions, and that is conditions, then effects, then interactions. What we've got here, this pending returns, is an effect, right? It's not interacting with the external world. It's just setting the amount that the message.sender has available to withdraw again to be 0, right? That's an effect. But we've put it after the interactions. So we've essentially got this in the wrong order. Now, what this opens us up to is a really tricky way of attacking the smart contract. So a malicious person or a hacker can attack this smart contract using something called a replay attack. And I think we don't have enough time to talk about it today, but I will go through it next week, what a replay attack actually is. But if we left this smart contract code like this, then someone could come in and withdraw all of the money in the whole contract, even the money that doesn't belong to them, using a replay attack. So this is bad. What we want to do instead is we can avoid a replay attack altogether by following the conditions, effects, interactions pattern. All right, so this is now okay. We'll set the amount to withdraw. You declare the pending returns in withdrawal method. Does it contain the same value in withdrawal method? So I'm actually not declaring pending returns. I'm getting from it here. So pending returns is a mapping that we've created in the smart contract storage up here. So in this withdrawal method, first I'm looking up a value in it. So I'm taking the sender of this transaction and I'm looking up how much they have to withdraw and storing it in an amount variable. Then later on, I am zeroing out that value. So I'm going to the pending returns storage mapping. I'm setting the amount to withdraw for whoever called this transaction to be 0, right? Because they have taken all that money out. They don't have anything left to withdraw, except if the payment fails, in which case I essentially refund them. So I give them back that amount to withdraw. So because I'm not creating the pending returns in this function, it's a storage variable, so it's going to stay across transactions. However, because we have declared this amount, which is a number, this amount variable will be destroyed at the end of the transaction. It's only part of memory at the moment. Does that make sense? Okay, cool. So the moral of the story is we have completed our auction contract. Right, so this is a bit bigger than the previous one, but it's already quite a useful application of blockchain, right? You can do a proper auction where anybody in the world can participate. You know, you don't have to rock up outside a house at 10 a.m. on a Saturday in order to place a bid on it, right? You can do it from any computer around the world. There's no kind of laws restricting who can participate in the auction. It's kind of open to anyone with Ethereum. It's democratic. The highest bid wins, and you can make sure that nothing shady is going on. You know, say the highest bidder looks a bit weird and someone doesn't like it, right? The contract will enforce who wins, and that's that. The code has become law in a sense. So that's a really cool way of, of using smart contracts to open up opportunities to people who previously didn't have those opportunities. So I know we only have 14 minutes left. So what I really want to show in this contract is the kind of current problem with how work is distributed, and then how we can spread that work around a little bit more. So you'll notice that anytime we want to get the highest bidder, we have to do a bunch of work, right? We have to loop through all the bids that have been made so far and find the highest one. What we can do instead is split this work up so that it's kind of updated in incremental pieces rather than all at one time. So in the last contract, we converted our array to a mapping, and that wouldn't necessarily work in this contract, because if we just had this mapping of bids, there's actually no way to iterate over that mapping. So there's no way to say, show me all values that have been set in a mapping. You have to know the key and go in and look at it. So we wouldn't be able to know who had actually put in a bid already. So what we have to do is get slightly fancier with how we're calculating our highest bidder. What I'm going to do is, instead of having this get highest bidder function that looks at all the data and kind of calculates the highest bidder, I'm going to store the current highest bidder and update it over time. So to do that, we'll add a tiny little bit more up here. We're going to have the address of whoever is currently the highest bidder, and we're going to have the current highest bid like this. So that's all we need, the highest bidder and the highest bid. Now our bid logic here becomes slightly more simple. So we still need to check if the auction is ended. We still need to check if there is a highest bidder, but that simply becomes message.value is greater than highest bid, which is a member of the contract. It's in the storage, so we don't need to do any lookup at all. This is now an O1 operation, bid is too low. So if we get to here in the effects section, we are the highest bidder. So what we can do is override the highest bid with message.value, and highest bidder is message.sender. And this is getting stored in the storage. We can remove our old logic for it, and we'll emit this highest bid increased. So that's quite cool. And let's delete this whole get highest bidder function. So we don't want to do any looping anymore. Okay. That's that. Now in auction end, we don't need to do this looping anymore because we've got the highest bidder. So we'll just delete that. We'll do that transfer. But we can again see more work that is being done all at once. So in this auction end function, whoever calls this has to pay for this loop here to calculate the withdrawals for everybody who wasn't the highest bidder. We have to ask ourselves every time we see a loop, how can we spread this work out? What if there was a way to calculate the pending returns incrementally rather than doing it all at once at the end? And there is, it's really easy. So I'm going to remove it from this auction end to start with. And what we kind of notice if we think through the logic of this is that if someone makes a bid that's too low, it gets rejected. if someone makes a bid that's higher than the previous bid, so they've got the new highest bid, whoever had the previous bid needs to be refunded, right? So we know that in this bid function. What we can do here is we can actually spread out the work by constantly updating that pending returns mapping when someone makes a new highest bid. So here we can just do pending returns. Oops. So if I look here, pending returns for the current highest bidder. So before we change the value of highest bidder to be the message.sender, they now have their old bid to withdraw. Right? And we can do that like this. So we're adding on whatever the current bid is to the withdrawal amount for the highest bidder, and then we're changing the highest bid and bidder. Hopefully that makes sense. I've said the word bid a lot. We'll also just do a check to make sure that the highest bid is not 0, because it will start at 0 and there won't be anyone to withdraw it. That's easy. Okay, so now we can see our auction end function is actually really simple. All it does is transfer the highest bid amount. Right, that's super simple. And then the withdrawal function stays exactly the same. Right, where we're doing that pending returns, we're zeroing it out and then we're sending the money. But what we've managed to do is move all of that work that was in one function, auction end, and that was also every time we wanted to check the highest bidder, we had to loop through, and we've amortized that. So we've spread it out into the bid function so that every time bid is called, it does a little bit of that work and it updates our information in storage so that we always have the latest value. And what we'll notice here is our previous way of storing bids is now completely unused. So we actually don't need to store who has bidded in the past and what their amounts were. Because everything is updated, that's already stored in these 3 variables. So we can delete that and save ourselves a bit of memory. Like that. Okay, and with that, that is kind of the amortized work principle done. So today we've covered essentially, the start of how to develop in Solidity. We'll go into a lot more detail because there's lots of little things that trick you up. And then we've done 2 out of 4 of the smart contract principles. So choosing efficient data structures to make sure that your smart contracts don't cost too much and that they won't hit the gas limit if you're not careful. And then again, spreading work around so that one person or one function doesn't cost heaps and heaps and heaps. We've talked a little bit about conditions, effects, and interactions, but next week I will talk more about why that's important in terms of what a replay attack is and how to defend against a replay attack. So we'll illustrate this one in a lot more detail. And we'll also talk about state machines and how we kind of first go through the design phase before we start writing any code at all. But with 7 minutes left, I'll just pause for any questions and then we can wrap up. So if you have any questions, now's the time.
Kayl, will you be providing us with the code repository?
Yes, yeah, I'll do that straight after this and send it in Telegram or WhatsApp. Yeah.
Thanks a lot.
Cool. Okay. Remember, if you've got any more questions, post them in the group. But otherwise, I will send a link to these contracts so you can have a play around. And then we will be back next week.
Thank you. Thank you so much.
Cool. Thanks, everyone.